So on the 4th of July, there was an announcement at CERN that was reported not only in the New York Times, but in many other newspapers and press articles, that physicists have found the elusive particle seen as the key to the universe. So this is pretty big language here. And here's the subcaption for this figure. Scientists in Geneva applaud the discovery of a subatomic particle that looks like the Higgs boson. And you'll notice, I hope today, that both Howard and I are going to be very, very careful not to say we found the Higgs boson, but we found a Higgs-like particle, a new particle, something that really looks like the Higgs, but we're not sure yet. So that's part of the fun of the game here. So one of the reasons that we're so excited is that this particle was predicted somewhere around 1964. In 1964, Peter Higgs, along with another of other theorists, invented a mechanism. And this mechanism evolved over time into something that we now understand to be called the Higgs mechanism. And this mechanism requires that there be a physical particle, which we call the Higgs boson. So we've been talking about this particle really since 1964 here. Okay? And the reason we've been talking about this particle is that particle physicists have something that they call the standard model. And what do we mean by the standard model? It's something that's really very, very simple. It's a model that describes the interactions of particles and their interactions. And these particles are the elementary particles. So to the best of our knowledge, the particles in this chart here have no substructure. They're what we call elementary particles. And there are two types of particles. The particles over here have what we call spin 1/2, and the rest of these particles have what we call spin 0 or spin 1. So the quarks here, the up and the down, have electric charge 2/3 and -2/3. So the protons, 2 up quarks and a down quark. The things we call leptons consist of the electron, which has negative charge, and 2 heavier copies of the electron. And then there are 3 neutrinos, which are very, very light. So in our standard model, we have only these particles here, and they're point-like. They interact by force carriers, which communicate between the particles. And in the center of this picture is this Higgs boson. So everything in this chart here has been observed experimentally until the Higgs boson. So the Higgs boson was the last piece of this model, and we think we've now found it. Okay, so to understand these forces, there are 4 forces: electromagnetism, weak, strong, and gravity. We don't understand gravity very well, so I won't talk about it. So that's a good approach, right? The other 3 forces we do understand extremely well. There's electromagnetism, which explains electricity and magnetism. And electromagnetism, we believe, is carried by the force carrier, the photon. The photon is a massless particle, and it interacts at an infinite range. So the light coming from the sun all the way to the Earth would be an example of the photon. The weak force explains radioactivity. For example, why neutrons decay. And the weak force is not an infinitely long-range force. We know that the weak force gets weaker and weaker with distance. And the weak force is carried by a heavy particle, the W and the Z boson. The strong force explains why the quarks are bound in the protons. And this is, of course, what we study here at RIC. Okay, so the forces are associated with particles. So the force carriers are the gluon, the strong force, the W and Z bosons. Remember, this word boson just means that the spin is integer, and the photon. The gluon and the photon are massless, but the W and Z are very, very heavy. The W is about 82 times the mass of the proton, so it's very, very heavy. So the real question that particle physicists, starting with Peter Higgs, have been trying to address is why are the W and Z heavy, and why are the gluon and photon massless? So we say that this is an example of a broken symmetry. If things were symmetric, everything would be massless. But the fact that the W and Z are heavy is a real puzzle to us. And this Higgs boson, Higgs mechanism, whatever, was invented solely to explain this problem, to explain to us why the W and Z are heavy. Okay, so what is this thing we're talking about that we think we found? Well, it's a particle, the Higgs boson, and it's a very special particle. It was invented to explain why the W and the Z were heavy, and all of its properties are predicted except for its mass. That means that I can calculate everything there is to know about this Higgs particle except for its mass. So I can make lots and lots and lots of predictions. And it's a real physical particle which we can study. Okay? It's also a field, so we do this in quantum mechanics. We go back and forth between particle and fields. So sometimes we'll say it's the Higgs field, and we envision that when other particles, say the W and the Z, interact with the Higgs field, they become massive. And it's not just the W and the Z, but all the particles in my little chart, the elementary particles, get their mass through the interaction with the Higgs. So for example, the top quark, which is pretty heavy, interacts more strongly with the Higgs than the electron, which is pretty light, which interacts less strongly with the Higgs boson. Okay, so what if there weren't any Higgs boson? Then all these particles would be massless, including the electron. The Higgs explains why the electron has mass. So for example, if you think back to your chemistry class where you had, say, a nuclei here with atoms at the middle and the electrons are zapping around the outside, the radius of this atom is proportional to 1 over the mass of the electron. So if the electron were massless, the atoms wouldn't form. You need the Higgs boson. So how does this mechanism work? Well, there are a lot of really bad analogies for how it works, and here's one of them. So none of the analogies are really too good, I don't think. So imagine that you've got a room, and it's full of physicists. It's sort of like space filled with the Higgs field, and the physicists are just taking up space. Okay, so into the room comes a famous physicist. Mary Kay Guyard actually did some early work on the Higgs boson. She was a summer student at Brookhaven. So the famous physicist walks into this room, the rumors start, and people kind of clump together to see what's happening. Okay, pretty soon she can't move at all because she's got all these admirers around her. So it's just like a particle moving through space, interacting with the Higgs boson. It attracts mass as it's moving through space. Okay, so the Higgs was invented to explain mass, but we should remember that it doesn't explain all mass because 95% of the mass in the universe up here is dark matter and dark energy, which probably has nothing whatsoever to do with the Higgs boson. So we're talking about this 5% of visible matter down here. And we're not even talking about all that 5%. For example, the proton, which we study here at RIC, gets its mass from the self-interactions of gluons. So we're really talking about the elementary particles in that chart I showed you, the electron, the muon, the quarks. Those are what are understood by the Higgs mechanism. Okay, so I said that we had a standard model, and it's actually a pretty simple model. You can write it on the blackboard just like that. That's pretty much the whole model. And it's a real model in that I can calculate, I can make predictions. However, if I take the Higgs boson away, my calculations are infinite. So the theory not only needs this particle, but doesn't make any sense unless it has something like a Higgs boson. Without something like the Higgs, when I start calculating, I get infinity. So for example, I can predict the W mass, which has been quite well measured, get 82 GeV, which is about right, but then I get infinity. So we know this is wrong. So we put the Higgs back in the theory, and what happens is we get a prediction, 82 GeV, plus a logarithm which depends on the Higgs mass. So for the last 30 years, physicists have been trying to infer what the Higgs mass might be by fitting data to their predictions. And so we infer from many, many measurements that the Higgs has to be less than about 145 GeV, if this whole can of worms we've constructed makes sense. So the discovery of 125 GeV Higgs boson makes us happy because it's completely consistent with our expectations. So the story now turns to the search for the Higgs. We started it at LEP, didn't find it. We looked for it at SLAC, and then most recently we looked for it at Fermilab, and none of these places were the right tool. Because if you remember the old story, E equals mc squared, you want to make a heavy Higgs, you need more energy, okay? So the Tevatron energy was about 2 TeV. The LHC energy is about 8 TeV, so it's about 4 times as much. So the tools to find the Higgs are the accelerator, the Large Hadron Collider at CERN near Geneva. The detectors are 2 big ones, ATLAS, which Howard is a leader of, and CMS, and Theory, which has pointed the way to look for it. So how do we make a Higgs boson? Well, at the LHC, the protons collide at 99.99999% of the speed of light, and most of the time, you don't make a Higgs boson. But very rarely, you'll make a Higgs boson, and it's going to decay in 10 to the minus 22 seconds. Remember, I told you you could calculate everything. Decays in 10 to the minus 22 seconds. So we can calculate how many Higgs bosons are made and what they decay to. And the way we're going to look for them at the LHC is by looking for the decay to 2 photons or the decay to 2 electrons and 2 muons. And these are pretty pictures of what happens in ATLAS. Okay, so wait a minute. I just told you that the Higgs has something to do with mass. So how does the Higgs interact with a massless photon? Well, it actually is an example of quantum mechanics. So we make the Higgs. Before it decays in this 10 to the minus 22 seconds, there are quantum fluctuations of these heavy W's, the heavy Z's, and the top, which is quite heavy, and then it decays to 2 photons. So it decays indirectly. And about 1 time in 10 to the 4, it'll decay to 2 photons. So we can calculate. So suppose this thing we made at the LHC were a Higgs. Suppose it were 125 GeV Higgs. So we would have made 174,000 Higgs bosons in the last 2 years there. Sounds like a lot. Well, 397 of them would have decayed to 2 photons. And it's really 397, not 398 or 396, because we can calculate pretty accurately. Of these 174,000, 10 of them would have decayed to 2 Zs, which then decayed to electron and muon pairs. 60% of the time, this Higgs decays to bottom quarks, which are very hard to see at the LHC. So the discovery of this particle is really based on these small numbers here. Okay. So how do we do it? We do it by what I'm going to call bump hunting. The Z boson weighs about 91 GeV, and it's been well studied over the years. So this is a plot showing the Z decaying to 2 electrons. So we measure the energy of this positron. We measure the energy of the electron. We measure their momentum. And then we construct a mass here. And this mass is the energy of the positron and the electron squared. And this is actually a vector sum here. And we construct this quantity and plot it. And it's got a nice bump at the Z mass. And so that's how we would observe the Z, by looking at this bump right here. So we want to do exactly the same thing for looking for the Higgs decaying to, say, 2 photons. So we want to measure the energy of the 2 photons, their momentum, and construct a nice bump like this. Well, you can already see that it's going to be very, very hard. Okay, look at these numbers. This is about 30,000. I just told you we made about 390 photons, so we're way down here on a plot like this. This width here, how wide this bump is a characteristic of the particle. However, the photon, since we can calculate everything, is really very, very narrow. So it would just be like a delta function on here. So what we're looking for is a little bitty thing down here in a plot like this. So when you look for the Higgs, it's not as easy as the Z because the Higgs bump is very, very narrow. And there are lots of 2 photons floating around from other sources. So it's like looking for the needle in the haystack. So now we turn to the detective story, and Howard is going to explain to you how it is that we found this. So in my mind, this is pure science at its best, this discovery of the Higgs-like particle. So Howard?
Okay, I'm very happy to be able to explain this to you, and a lot of the things that Sally said you're going to hear in my talk. So it's good. We always, for particle physicists, we always enjoy having repetition. You'll see some repetition in the talk. I had a handout outside for those of you who have got it. I'm going to refer to some things in it which you should really know. So I thought you would never remember them, so I put them in the handout in case you need to refer to a couple of pieces of information. So the discovery, is it the Higgs? Well, how did we do it? As Sally said, there were 2 seminars given from CMS and from Atlas on July 4th. It started about 3 o'clock in the morning, New York time, and I was happy to be able to listen to that. And as of July 13th, there were about 5,000 print stories, 1,000 television spots worldwide. It was really amazing how this picked up. Even The Economist had the cover about a giant leap for science. Made us feel good. And next week, there will be the first publications of this data. And for the particle physicists in the audience, please refer to those publications because the data in detail will be described in the publications. I'm going to kind of give an overview. So my interest in this subject started in the 1970s when we were planning to build a machine here called Isabel. And the same question that Sally mentioned, why do particles get their mass, was the question that we were asking in the 1970s. Well, Isabel turned into Rick, and I started working at the CERN intersecting storage ring. I worked at the Deviation at Fermilab. I worked at the superconducting super collider in Texas, trying to answer this question. And finally, I started working at the Large Hadron Collider at CERN. So coming to this conclusion that we've actually found something is a very good satisfaction in my career. I'm going to discuss the Atlas experiment, how it was designed to find the Higgs. I'll mention computing because Brookhaven's Tier 1 Center is the largest in Atlas. I'll explain the physics results that we have right now, and I'll explain how we're planning for the future because, in fact, we're not finished yet. We're just beginning. So things to remember from Sally's talk. All of you heard Sally's talk. You were listening very closely. Here's a few little details that I want you to remember. So bosons have integer spin. It could be 0 or 2. Vector bosons have spin 1. And Sally talked about the photon, the carrier of the electromagnetic force, the W and the Z, the carrier of the weak force, and the Z decays into 2 leptons, and I'll be mentioning this, the Z decaying into 2 electrons or 2 muons. And fermions have spin 1/2, and those include the quarks, the leptons, the electron, the muon, and the tau, and their neutrinos. And the reason I go into this is if this particle that we have observed is really the Higgs, it must decay into all of these particles with a well-predicted rate into all the particles. So before we know it's the Higgs, we have to measure its decay into all these different things. Okay, lesson number 2, standard deviation. You'll hear about some kind of sigma later in my talk, and so I figured I ought to tell you what standard deviation means. This comes from all fields of science, so I went to the source of all knowledge, Wikipedia. Wikipedia, the article there starts out this way. I couldn't believe it. Particle physics uses a standard deviation, a standard of 5 sigma for the declaration of a discovery. At 5 sigma, there is only one chance in nearly 2 million that the result is wrong. That is, the measurement seen as a random fluctuation. This level of certainty prompted the announcement that a particle consistent with the Higgs boson has been discovered in 2 independent experiments at CERN. This is pretty up to date, right? Wikipedia, you have to look hour by hour to see what's going on. Okay, so this is what's called a sort of normal distribution. When you measure something, it has a mean, that's mu, and the precision with which you measure it is called sigma. So 1 sigma is shown here. 1 sigma covers plus or minus 1 sigma, has about 68% of the probability that you measure, the measurement of that thing that you're measuring is within this point. And then if you go out to 2 sigma, 3 sigma, 4 sigma, 5 sigma, you can see the probability of what we're going to say the background fluctuating to be what we observe is very, very small, 2 parts in 10 to the 6th. Okay, so that's standard deviation. Now, Sally also talked about invariant mass, and I want to use this concept also. She showed you the mass, the Z decaying into 2 electrons. The invariant mass is what happens when you have a particle which decays, and let's make it simple, just into 2 particles, and you use this equation to calculate the mass. This is actually the mass squared. And so if we measure the products of that decay, we can see a distribution like she showed you, and I'm going to show you some other distribution. The mass resolution is how well do we measure the invariant mass. The smaller the sigma sub m, the standard deviation of the measurement of the mass, the better the resolution. And this is important because when we began to think about how to discover the Higgs when Atlas was being designed, we didn't know a lot. We didn't know what the mass was going to be. It could have been anything. But we knew that it was above 114 giga-electron volts. That's 10 to the 9th electron volts. And if the mass were about 126, and I won't go through all the different possibilities, but let's just pretend it's 126, then we could have known that the channels that we should look for, as Sally said, are Higgs decaying into 2 photons or Higgs decaying into 2 Zs, which would go into 4 leptons. And the reason we would look at those first is because they have good mass resolution. They have small values of sigma sub m. So we can measure with precision a peak in that mass distribution. There are other channels which I won't talk about, which have moderate mass resolution or poorer mass resolution, and we'll get to those, but we need more data. Okay, so the ATLAS experiment, ATLAS stands for a toroidal LHC apparatus. That's what the ATLAS acronym means. It's at the Large Hadron Collider, located at CERN in Geneva, Switzerland. It's large because it's 27 kilometers in circumference. The design is 14 tera electron volts. That's 10 to the 12th electron volt proton-proton collisions. Why do we take proton-proton collisions? Because we can get a bottle of hydrogen gas, and hydrogen has 1 proton and 1 electron. We can strip off the electron, and we can collide protons together to produce our Higgs particle. Now, the design of the machine, this 14 TeV, hasn't been realized yet. We ran at 7 TeV in 2010 and 2011, and at 8 TeV in 2012. It turns out that we're doing much better than we expected. The machine has been running spectacularly. there are bunches of protons, 10 to the 11th protons in a bunch, and about 1,500 bunches around the machine. And we ran at a spacing of about 50 nanoseconds, or about 50 feet. So there's a bunch of protons here and a bunch of protons here. They collide. Not all of them interact, but up to maybe 35 interactions could occur per crossing, even though there are 10 to the 11th protons. And this shows us one of these events in our tracking detector, and you can see different vertices which occur across what we call the diamond of the interaction region. In this particular case, there's two muon events. This is a Z event into two muons. We can tell that from other parts of the detector that are outside, but it's a sort of a complex environment. So this is a photograph, an aerial view of the CERN laboratory. The laboratory is actually located over here. This is the airport where we come in when we land, Lake Geneva, the Jura Mountains, and the Large Hadron Collider is underground and goes between Switzerland and France. There are 4 major experiments there: ATLAS, LHCb, CMS, our sister experiment, and ALICE. Now, the LHC tunnel is filled with magnets, and these magnets, you can see a curvature here. I'll show you a little bit more what the inside of the magnets look like, but some of the magnets in the machine are built here at Brookhaven. This is showing one of the magnets is on its way to the LHC some years ago. Okay, so as Sally mentioned, we use E equals mc squared. The higher the energy, we can produce these heavy particles. The magnets themselves are so-called 2-in-1 magnets. This is an idea that was invented here at Brookhaven. There are protons that are, let's say, going into the board in this tube and coming out there, and they are coming together and colliding at the different intersection points. I'm going to show you an animation later, and so I'll just go through this while it's static, easy to see. Challenge in a few minutes. So there's a linear accelerator that starts the protons along their acceleration path, going into a booster, the proton synchrotron, into the superproton synchrotron, and eventually into the Large Hadron Collider. And these proton bunches are caused to intersect at the center of these various detectors. The machine has worked fantastically. We last year thought we would get about 1 in these units of inverse femtobarns, but we got close to 5. In 2010, the total amount we got was down here. You can't even see it. And this year, in 2012, we're doing even better. It's only July, and we're already exceeded what we did all of last year. And this curve will probably go up, and by the end of the year, we'll probably get maybe 4 or 5 times as much data as we have right now. The total data that we produce is astronomical, and I won't go into this, but it's as if there were a 1,500,000,000 gigabyte disk hard drives worth of data being produced. So how are we going to produce the Higgs? So I told you we have protons. We use protons because they're easy to get, they're easy to accelerate, and we can collide them. But as Sally mentioned to you, protons are made up of 2 up quarks and a down quark, and there's a lot of gluons in the proton. So this is meant to be a proton, and here's another proton. And you can imagine occasionally 2 of the gluons from those protons come together in this top quark loop, produce the Higgs boson, and then it decays through another loop into, for example, 2 photons. We knew this was a possibility, and so we designed our detector to be able to see events where there were 2 photons. So let me tell you a little bit about the ATLAS collaboration. It's a huge scientific endeavor. It has about 3,000 active scientists, about 1,800 have PhDs, and about 1,200 students, 174 institutions, 38 countries. There are 44 institutions just in the US. We're the largest single country in terms of participation. And this is the map, and you can read all the names of the institutions. In the US, there are about 376 PhDs, There are 39 universities and 4 national laboratories participating in the experiment. And these are statistics about the total number of people, about 700 people altogether. It's kind of interesting. Most of the postdocs are at CERN. The students spend a year or 2 at CERN and then come back to their home institutions. And most of the faculty stay at home where they have teaching responsibilities. BNL has had a tremendous impact on the ATLAS experiment, and I only have one slide to tell you this, but there are over 50 people from Brookhaven that have contributed to ATLAS in the physics department, instrumentation division, magnet division, collider accelerator department, travel. We do a lot of travel. Procurement, legal, fiscal, public affairs, all sorts of people at the lab have helped on this. We built part of the liquid argon calorimeter and the cathode strip chambers for muons. We work on physics analysis. We had one of the Higgs group co-conveners. We do maintenance and operation of the detector. We work on performance so that we understand how well the detector performs. We work on the trigger, which I'll define for you in a minute. Computing, I mentioned the Tier 1 center. And we're now working on upgrades for the detector. We're the host laboratory for US ATLAS. And we have many leadership positions in ATLAS and in the US. So what does ATLAS look like? Well, it's very hard to imagine this detector unless you've actually seen it in person. You have to go and take a tour, and right now that we're running, you can't go down and see the detector, but it's pretty impressive. It's a real wow. The detector itself is about 150 feet long and 40 feet in radius and weighs about 7,000 tons. And as I like to say, if you wrapped it in cellophane, it would float. So that's good to know. This is the size of a person, so it's really huge. And the toroidal, the name toroid comes from the magnetic field that's produced by these big coils. There are 8 of these around in a circle, and there are some toroids in the forward direction, and they're used to measure the muons. Now, the detector is located about 100 meters below ground in a cavern. I said the LHC was underground, and this gives you a picture of the detector as it was going together. And these are some of the muon chambers, the cathode strip chambers that we built here at Brookhaven are right here in this picture. But this is just one piece of the detector. Now, even the Muppets know about ATLAS. For those of you who saw the Muppet movie, it was featured for a good 1 second. You had to know when to look, but I saw it. Some people use Lego to build their ATLAS, and you can buy a Lego set if you want to do your ATLAS at home. But for the rest of us, we have a pop-up book, and I have the pop-up book here if you'd like to see it. And you can put together your own version of the detector right here. And if anybody would like to see it, I'll show you. And I have a web link later on that shows where you can buy it on Amazon. Okay, how does the detector work? So I want to show you how it is that we can design a detector to actually see the Higgs boson. So this is a sort of generic detector. It's made like an onion with different layers. There's an inner detector, an electromagnetic calorimeter, a hadron calorimeter, and a muon spectrometer. And this is the way different particles look like when they go into the detector. An electron, for example. Electron is a charged particle. So in the inner detector, which has a magnetic field, we see the track, and it curves because of the magnetic field, and it produces a shower in the electromagnetic calorimeter. So we measure the energy and compare it to the momentum, and we can identify it as an electron. The photon, however, doesn't have any charge, and so when it goes into our detector, there is no track, no charge track, and there's energy in the electromagnetic calorimeter. This is a very simple concept, but I like to say there are plenty of seats, by the way, for those of you who are standing in the back. There's a lot of seats. You can come up and sit down, be more comfortable. So there was a workshop, one of many workshops this spring, where people in ATLAS spent an entire week studying the details of separating and measuring electrons and photons. So there's a lot of details that I'm glossing over, but this is the basic concept. Okay, so protons are charged particles which give energy in the calorimeter. Neutrons are another particle which doesn't have any charge, and so there's no track, but there's energy in the hadronic calorimeter. Muons are charged particles, so we see the track. It doesn't give much energy in the calorimeters, but we measure its momentum in the muon spectrometer. And this white thing here is something which I'm not going to really talk about much today, but there can be neutrinos which don't interact with the detector at all, and we infer the neutrinos by missing transverse momentum. Now, Brookhaven actually brought the idea of using very thin strips to the electromagnetic calorimeter concept. And this is a picture dating back to the 90s, in a previous experiment that we did at the SSC, actually. But these fine strips bring two features. It allows us to measure the vertex of the interaction with the two photons, and I'll show you what I mean by that. And these thin strips help veto the pi zeros, which decay into two photons and are a big background. So here's an event display, and this is something we could talk about for a long time. In this case, the proton is going into the board here, and these are various charged particles that are coming out of the collision, and they have a curve because they're in a magnetic field. Here's the electromagnetic calorimeter, and the yellow indicates some energy there. And here's the other electromagnetic calorimeter deposition. And there's no track going to either of those, so those are two photon candidates. And if we take a view of those two events from the side, the photon is coming in and gives a little bit of energy in the fine strips, and then more energy in the back of the calorimeter. And by measuring the direction between the back to the front, we can extrapolate the direction of these two photons and tell where the vertex is. And I showed you the event that had maybe 35 different vertices. So knowing that the two photons come from one of those vertices is a real strength of the Atlas detector. The trigger. Trigger is crucial for selecting events, which could be the Higgs boson. Because every time there's a collision of proton bunches, we get every second about 500 million collisions. And we can only write about 400 of these out for future analysis. We can't actually save all of them. We have to figure out which of the possible events we should save. It's less than 1 in a million. In fact, this is only the beginning of the needle in the haystack argument that Sally mentioned. If we don't choose correctly, we lose those events forever. So the trigger must be very selective and very efficient. So we choose the topology, and if we're looking for Higgs going into 2 gammas, we look for something that has electromagnetic energy deposition and no tracks pointing to it. So we do that at the trigger level. And this is there is a 3-level trigger system which selects the events that are possible. Once we have the events selected, we have to do further analysis. And this is done in the computing area. And the computing in the Atlas experiment, like all the LHC experiments, is distributed. CERN has the center, the Tier 0 computer center, but Brookhaven has the largest Tier 1 center. And also in the US, there are 5 clusters of Tier 2 centers distributed around, and we do all the computing remotely. It's been spectacular, not just for analyzing the data, but also for simulating the backgrounds, and I'll show you some of the simulations later on. Okay, so we're ready to talk about data now. So here is a data plot of the Higgs candidates that decay into 2 photons. This is data from 7 TeV and 8 TeV, so the data from last year and this year. And what you notice is that there's just a little bit of a bump here compared to what you might expect if you fit the background. And we fit the background to some curve, and if we subtract the data that we see from the background, this is the background subtracted data, and you see these events that Sally talked about. Was it 176? We're supposed to 397. I know I didn't get the right number. That's how many events are in here. Actually, there's a little bit more, and we'll talk about that too. So we have been studying this data for a couple of years. We had a little hint of an excess in 2011, and in the 2012 data, we also have an excess, but just about in the same place. If we add the data together for 2011 and 2012, we have this excess. From the data, we can exclude regions of this mass region, of the mass spectrum, because we're plotting here the mass of the two photons. We exclude data from 112, which is below what LEP saw it, up to 123 GeV, and from 132 to 143 GeV. So that these are, it's not, we've excluded the possibility that a Higgs candidate would be in these regions that are black, but the region here is not excluded. So then we did an analysis, a very statistical analysis, which I will defer for the moment, but tell you that this curve, this black curve here, shows the probability that the background varied in order to explain the excess. That is, in this plot, what's the possibility that this background was not at the level which it looks like here, but it goes up to follow this peak. And that statistical analysis says that that probability is about 4.5 sigma. So this is 2 sigma, 3 sigma, 4 sigma, 5 sigma, so about 4.5 sigma. So already just in this one channel, the 2 gamma channel, we see evidence for a new particle of about 126 GeV, and the local significance, as we call it, is 4.5 sigma. Now, in fact, there's another thing called the look elsewhere effect. It's not just at the place where you think you see the deviation that you have to think about, but you have to think about how many times would there be some fluctuation somewhere else, and that reduces that significance to about 3.6 sigma. So interesting, but not sufficient to call it a discovery yet. Well, now I'd like to change the subject to the next channel, 2 Z bosons going to a positron, electron, and 2 muons. And I have this little animation to show you. So we're going to watch protons being accelerated here in the booster, then in the proton synchrotron up to 25 GeV. It goes then into the super proton synchrotron at 450 GeV. And you see the bunches of protons. Then they're going to be injected into the Large Hadron Collider. And you see the 4 experiments. And now we're going to go into the ring and follow the magnets. So here are the magnets. The standard model was written on the wall, in case you remember. We're going from France into Switzerland. We're following these rings. And now we have a proton. You remember the 3 quarks? They have 3 different colors. So here's the proton coming up to the Atlas detector. You see 1 proton here. And if you look on the other side, there's going to be another proton. Here's the other proton coming into the center of the detector. They collide. A spray of particles is produced. And in this particular event, you'll see one electron here because there's electromagnetic energy deposition with a charged particle that points to it. There's another electron here, again, a charged particle pointing to this electromagnetic energy deposition, and 2 muons. Okay. Okay, so now I want to plot the invariant mass distribution of these 4 leptons. And the case we have are 2 electrons and 2 muons, or 4 muons or 4 electrons. And this is a little more complicated plot, so let's take a minute or so to understand it. The data are these black circles with error bars, and the error is the 1 sigma variation. So there are, in this particular bin, I just happened to notice at 125 GeV, there are 13 events, and the background in this is about 5.5 events. And you can see, therefore, from the error that the signal is above the background, and it's a few sigma above the background. If we look in other regions of the invariant mass spectrum, and this is a little complicated, this plot is complicated, but I didn't want to change the official Atlas plot. This blue line here is what a signal would look like for 125 GeV Higgs boson. So we see just a little bit more than maybe would be expected. but the background is really over here. And this would be what would be if there were 190 GeV Higgs boson. We don't see in excess enough to explain this. So we don't say that there's 190 GeV Higgs boson. And this would be a 360 GeV Higgs boson, and we don't really see evidence there either. So the only place that we really see in excess is at 125 GeV. Now, we do a statistical analysis, and you remember what the standard deviation is. And again, we plot the statistical significance that the background in that one bin exceeded. The background would come up to where we see the data, and that is about 3.5 sigma. And the mass is about 125 GeV. So again, this is a different channel. We see some kind of evidence that there's something going on. So the next thing to do is actually to combine the results from the 2 photon and the 2Z into 4 lepton, and we see the excess again. And in this particular case, combining these two channels, the significance exceeds the 5 sigma point. When this happened at CERN, when the seminar was being given, Fabiola Giannotti, our spokesperson, was giving the talk, and the audience, when she used the word 5 sigma, you saw on Wikipedia how important 5 sigma is. Once it exceeded 5 sigma, the audience spontaneously erupted into applause. And she said, wait, I have more to tell you. Please let me continue. Okay, so this is the evidence we had reported on July the 4th. 5 sigma local significance with the expected value would be this dashed line. We would expect to see something at maybe 4.6 sigma. So like most discoveries, there's a little bit of an excess fluctuation that we see. We hope it's for real. Now this is another plot which I'd like to talk about. The different channels that we measure between the 2011 and the 2012 data that I haven't really spent much time on. The W and Z plus Higgs going into BB bar. We measure, this is the so-called signal strength, the value of the events that we see compared to what we expect. And you can see the error on this is very large, so we don't have a very good determination of the BB bar or the tau tau. But the 2 photon measurement has a much smaller error and is slightly above what we would expect it to be. The ZZ is about right on line, and altogether, this is very consistent with what we'd expect. So, what are the plans for the immediate future? We want to determine, as Sally said, whether this excess of events is the standard model Higgs boson. In order to do that, we have to measure precisely the ZZ star. We have to have more data for that, and the WW channel. We have to measure the decays to the fermions. We have to measure the spin. If it's a boson, it should be integer spin. Since it decays into 2 photons, we know it's not spin 1, but it could be spin 0 or spin 2, and we have to do some measurements about that. We expect perhaps 4 times as much data in 2012 as we have now, and this might be enough, but I'd like to be conservative and say we're going to have to plan on actually much more data. So this is a little bit of planning exercise that we have for the next 20 years. Not that we're planning for the next 20 years, but we're doing detailed planning for the next 20 years. Over here on the side are the years, so we're in 2012. In 2013, there's going to be a long shutdown to repair the splices in the magnets. I don't know if those of you remember, but in 2008, even before the 2 beams collided, there was an incident where the splices caused a small explosion. And in order to solve that problem once and for all, they're going to have to fix all the splices, and that's going to be done in this long shutdown. And there'll be a few other improvements to the detectors. And then we'll run at perhaps 13 TeV. And going to a higher energy will really improve the physics reach that we have. So we'll run probably until 2018 when there'll be another long shutdown, and we'll improve the detectors, our so-called phase 1 upgrade, to go to higher luminosity at maybe 14 TeV. And eventually there'll be another shutdown in 2022, and then more running. And this shows the total amount of integrated luminosity that we expect. We're aiming for something like 3,000 inverse femtobarns by 2030. So I'm at my conclusion, almost ready for your questions. Be thinking about your questions. The LHC physics program has observed a new particle at about 126 GeV, which might be the standard model Higgs boson. More data is required to measure all of the properties of this new particle. This will probably take several years. The running in 2015 and beyond will be at greater than or equal to 13 TeV, which will open a larger window for discovery of other new particles, the source of dark matter that Sally mentioned, perhaps supersymmetry. We're hoping for more discoveries than just this one. Now, in the handout, I have the essential websites. So Sally and my talk are found on the first website, in case you want to look at them again. We have a site at Brookhaven. There's the must-see LHC wrap. How many of you have seen the LHC wrap? You'll agree it's a must-see. You must see it. That's all I want to say. There's the Atlas public webpage where you can find more information about these results and lots of other links. We have a YouTube channel. There was an elegant essay by Larry Krauss in the New York Times a couple of weeks ago. There's the particle adventure if you want to learn more about the standard model. There are some virtual tours of the Atlas experiment. Here's the link where you can buy the pop-up book. And there's some video physics for the 21st century, some courses if you want to learn a little bit more. Okay.
Thank you, Howard. Thank you, Sally. So we have a few minutes for questions from the audience. Following the questions, then there's a reception in the lobby, so probably not all questions will be answered. Okay. And so if you still have more questions after the time we spend here in the auditorium, then Howard and Sally will be available in the lobby afterwards to also answer your questions. Could you bring up the house lights, please? So we can see raised hands coming up.
We answered all their questions.
Dr. Aronson gets first question.
If it's not the Higgs, how long will it take to show that it's not the Higgs if it's not, based on these measurements, and then what?
Well, I mean, I already got email from people that think it's something else. And so we have to make these precision measurements, as I said, for example, BB bar, tau tau, measure the spin, measure the exact branching ratios. As I said, I think it's going to take a few years. But this has been a gold mine for theorists having some new ideas about what it could be.
What happens is that the theories get more and more restricted. The more they do the measurements, the less freedom you have to put your ideas in, and pretty soon your model looks pretty much like the standard model. So within, I think, a couple years, we'll be pretty pinned.
Yeah, we'll have a huge amount more data, as I said, 4 times more data by the end of this calendar year. And one of the really interesting things, which I didn't mention, is that the end of the time we take the data from there until we are able to analyze it and get some results is really less than a week. So that's because of the computing resources that we have at our disposal and the fact that there are so many people working on the problem. So the results come out rather quickly. So by early next year, we'll have the data analyzed from this year's run, and then we'll have an idea of what there is. But I suspect we'll need more data, and there won't be any more data until 2015. And that's why I say several years.
Second row.
The great triumph of the Higgs mechanism was that it avoided all the arbitrary masses of the fermions by replacing them with the Higgs coupling. In what way is this an advantage in that now we have all these arbitrary Higgs couplings?
You're supposed to repeat the question, by the way.
The question is, the Higgs mechanism was invented to give the W and Z mass, and in fact it actually predicts those masses. However, the masses of, say, the electron and the top quark are accommodated by this model, but not predicted. So we very much hope that there'll be something beyond the standard model which explains these masses. And of course, the LHC at the higher energies, we hope that maybe it'll find some clue. But it certainly doesn't explain why the top quark is heavy and why the electron is light.
On the aisle, halfway back.
Howard, do you think the Nobel Prize would be given for the discovery of the Higgs?
It's very hard to pick out 3 people out of 3,000. So, but maybe Peter Higgs will get the Nobel Prize. Plus, even the theorists, there were 6 theorists. I guess one is deceased, but there were more than one person that came up with this idea. So it's going to be difficult because of the problem of 3. If we could give the prize to 6,000 people, it'll be much easier.
Halfway back in the middle of the row.
Could you comment about the other detector and whether or not it's giving data which is consistent with what you
Yes. Yeah, CMS, the CMS detector has very similar data to ours. It's not identical. They have for those of us that were in the competition with various detector techniques, they have a different detector technique. We, of course, think ours is better. They think theirs is better. But the techniques are somewhat different, but the results are very similar. They have something like a 5 sigma discovery of something in exactly the same place, both in the 2-photon mode and in the ZZ mode. And they also claim something in the WW mode. So the data is very consistent, and that's what makes the whole thing much more believable. The 2 independent experiments doing the analysis by different people come up with something that's 5 sigma, very significant. It must mean that there's something real there. Yeah, I see. Mary's going to ask me a hard question.
No, it's actually a question for Sally.
Good.
Do neutrinos actually get their mass from the Higgs?
The question is, what about neutrinos? We didn't talk about them. In the simplest version of the standard model, the neutrinos do not get their mass from the Higgs, and that's easy to understand. A neutrino is its own antiparticle, so the neutrinos are intrinsically different from, say, the electron, which is not its own antiparticle. So there's still more mysteries out there for us to figure out, and the neutrinos are one of them.
One more question? Second row.
The question is, what about supersymmetry results? So as you probably know, I suspect you know very well, there's been no evidence for supersymmetry in the searches found either by ATLAS or CMS up to mass scales of about 1 TeV, 1 tera electron volt. However, there are 2 things to say about it. One is the theorists are very creative. There are 50,000 supersymmetry models, so we've only looked at the most simple models so far. So there's an attempt now to look at more at different models, and there'll be those searches that will be done next. The second thing is maybe we're below the threshold where you see it, and by increasing the energy of the Large Hadron Collider, we'll open up the opportunity to see higher mass supersymmetry particles. So we're not finished yet.
And
in both cases.
The other thing about supersymmetry is that the minimal version of it predicts that the Higgs boson is rather light, that it's less than about 130 GeV. So the fact that we've seen something which looks like a Higgs at 125 makes some theorists feel really good that supersymmetry is just around the corner at the higher energy. So it's not over yet.
Let's thank our speakers again.